Hello and welcome to video 2 of 2 for Chapter 7. Now in the first video for Chapter 7, we introduced the concept of voltage or the electric potential. In this video, I would like to look at the relationship between voltage and the electric field a little bit more closely. Specifically through the equation that we came up with last time that looks something like this. Delta V is equal to minus the integral from point A to point B of E dot dr. Now, if you remember, this came from the differential version of work. And originally, it was written this way. So, for the moment, I would like to consider an electric field that points strictly along the positive x direction. So, we'll say that this is positive x right here. Here's y. And what I'd like to do is to think of taking a charge here and letting it go. So this right here, we'll say, is going to be the direction of dr. This is also the direction of E. So, as drawn, you can think of E as having some sort of magnitude or being a function of something in the x hat direction. And dr is dx x hat. Now, when I do this dot product right here, what I get is E dx, because x hat and x hat are in the same direction. What I'd like to do is, instead of calling this E, I'm going to call it E sub x. Just bear with me here. So, I could think of dv here as being minus E sub x times dx. Or, if I move the minus sign to the other side and divided both sides by dx, E sub x is equal to minus dv dx. Now, let's imagine another electric field. This one, we'll say, points along the positive y direction. So here's our electric field. Here is the x direction right here. So x and y. Now, we could talk about the difference in potential between, say, here and here. Maybe you put a charge here and you release it and it goes this way. It's whatever view you want to take. But this right here is going to be the direction of dr in that case. And this is also in the direction of E. Now in this case, if I looked at dv and I did the same argument here, I would get minus E y dy. Or E sub y is equal to minus dv dy. You can imagine if I did the same thing for the z direction, I would get the same thing, except it would be Ez. So imagine now an electric field that has an x component, a y component, and a z component. It's a vector. Ex, x hat, ey, y hat. EZ Z hat. And you know, overall, the electric field's magnitude E might depend upon X, Y, and Z, all three variables. If I rewrite EX, EY, and EZ using this notation right here, I would get minus dV dx x hat plus minus dV dy y hat plus minus dV dz z hat. Now, x hat, y hat, and z hat are Cartesian unit vectors. They're constants. They have a length of 1 and they always point in the same directions. V itself is a scalar. It's a number. It's a mathematical function that has no direction. It's like potential energy, except it's electric potential. So typically the way we do this, the way we write this, is to pull the d by dx, the d by dy, and the d by dz out together and have directions attached to them. For example, and then you operate on the voltage with it. And the voltage might be a function of x, it might be a function of y, it might be a function of z. Now, this right here has a special name. We call it del, or the gradient operator. It's also called a directional derivative. And the way to think about it is that when you operate with this, you're asking, how much does my thing change along the x direction? How much does it change along the y direction? And how much does it change along the z direction? And what you get is a vector at the end of the day. Now, the way the del operator typically is written is as an upside down triangle with a vector sign over the top. Okay? So, here, just because of notations, the capital, not the capital, but the regular D that you see here, in d by dx, d by dy, and d by dz, is written this way, generally in the assumption that your mathematical function only depends upon x, or it only depends upon y, it only depends upon z. But since our function might depend upon different variables, we want to reflect that not by writing it as d, but by writing it as sort of a weird looking d like this, and this means partial derivative. Basically all it means is, like, if I want to take the partial derivative of something with respect to x, I just hold y and z fixed. I pretend that they're constants. So this is usually written the following way. D by dx x hat plus d by dy y hat plus d by dz z hat. So another way you could write this would be that the electric field is minus the gradient of the electric potential. And this is an incredibly important thing to know. So, what this allows us to do is to recover the electric field if we know what the voltage looks like. And as a simple example, just to show you how this works, I'd like to go back and look at an example that I did at the very end of the last video, where we had a hoop of wire, and we asked what the electric potential was, what the voltage was, a distance z above it. Now, I'm going to write down the result. The result that we got was that the voltage itself looked like lambda times A. Now, A, remember, was the radius of our hoop, divided by 2 times epsilon naught, the square root of z squared plus a squared. Now, we've done the hoop example before. We did it way back, I want to say, in chapter 5, in the very last video, where I integrated a whole bunch of electric fields to show what they look like a given distance away. I did an infinite line of charge, I did a line of charge that had a length of L, and I did a hoop. So the question is when you do this, do you get the same result that you did if you do the integral the hard way? So here, remember, the electric field is minus the gradient operator of V. Now, let's write this out. Minus d by dx, x hat, plus d by dy, y hat, plus d by dz, z hat, times, we're operating on V. V looks like lambda times A over 2 epsilon naught, the square root of z squared plus a squared. Now, if you look at this right here, if you look at what the potential looks like, the only variable that we have here is z. Z is how high above the hoop we were. A is the radius of our hoop. You could consider that to be a variable as well, perhaps, but x, y, and z here refer to the location that we're interested in and not the location of the charge distribution. So what that means is that were I to take the derivative of this with respect to x, holding z fixed, I would get 0, because none of this stuff depends upon x. It's all constants. If I were to take the derivative with respect to y of this, same thing, 0. But there's a z here. So when I take the derivative of this with respect to z, I don't get 0, I get something else. So these two right here give us 0 when we do that, but this one doesn't. So let's see what we get. So the first thing I'd like to point out is that you have a minus sign that sits out in front of all this stuff. I'd also like to point out that lambda, a, 2, and epsilon naught are all constants, and so is z hat. So I'm pulling lambda, a, z hat, and 2 epsilon naught out. And what I'm stuck doing now, since this is only a function of z, I can turn this partial derivative stuff into just a regular derivative. D by dz of z squared plus a squared raised to the minus 1/2 power. Remember, that's the same thing as the square root in the bottom. Now, when you do this derivative right here, you get minus 1/2, that comes down. You raise z squared plus a squared, you raise that to the minus 3/2 power because it's minus 1/2 minus 1. And then you have to take the derivative of the inside. When you do the inside, a is a constant, but z is not, so you get 2 times z by doing that interior derivative. Now if you take a look here, the half and the 2 are going to cancel each other out. I have a minus sign that sits out in front of here and a minus sign here. Those are going to cancel each other out. So what I get is lambda times a times z, z hat, because there's a z at the top. And in the denominator, I get 2 epsilon naught z squared plus a squared raised to the 3/2 power. Now, I encourage you to go back and look at that very last video in Chapter 5 and see if this is not the same thing that you get swapping out A for R, because we used R for radius there instead of A. What you'll discover is exactly the same thing. So what we have here is a tool to recover the electric field from the voltage. And since voltage is the thing that we end up measuring anyway, this is an incredibly powerful tool. Now, that said, I'd like to remind you also about something that we talked about in the last video. And that is, if you remember when we were looking at the net work around a closed loop due to the electric field, or not the electric field, but due to the electric force, I had pointed out that if you take and you do your integral along the part where the force is constant in magnitude, here was dr, but the force was working like this. The angle between was 90. You get 0. Now, here's what that means. If you were to try to move a charge along that path, you're not going to have to fight with the electric force along this, because the force doesn't change at all along it. Now, we call these types of things equipotentials. Now, if you go back and you look at the definition of, the electric potential and related to, say, in relation to the potential energy, it looks like this. Your voltage is what you get when you look at your potential energy over Q. But here's the thing. If the force is the same all along here, and your potential energy depends upon the force, then the potential energy along this is the same, which means delta Q, or delta U rather, is 0. So your change in voltage along this is 0 as well. Hence the part, equal potentials. It doesn't change. Now here's the deal as well. Work is equal to minus the change in potential energy. If delta U is equal to 0, that means that the work is 0 as well. So the electric force doesn't do any work along equipotentials. Okay? Now, that's actually incredibly important, because if you think about conductors, for example, wires are good examples of conductors. Everybody who has a house or has a car, has anything that's electrical that has wires in it. And, if you remember, in the previous chapter when we talked about Gauss's law, I used Gauss's law to show that the electric field on the inside was 0, and that very close to the surface of a conductor, the electric field is constant, okay, and it looks like sigma over epsilon naught. But here's the deal. We know no matter how curvy your surface is, as long as it's unbroken, if you zoom in close enough, it looks flat. Which means that the electric field is the same at all points along the surface, okay, in magnitude. And if you think of the relationship between differences in voltage, and this right here, if you think about moving along the surface, since it looks flat, your dr is going to be like this and your E is going to point out. And what that means is that conductors are areas of equal potential. Okay? Now, as a consequence, and we're going to discover this next chapter, we're going to talk more in detail about it too, is that if you look at this point right here, or 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 this point right here, any point along the surface of this conductor, the voltage is the same. So it takes no work, really, using the electric field to move a charge along the surface of the conductor. So if you wanted to move one from here to here, you're not fighting the electric field at the surface because it doesn't apply. It takes no work for you to do it, at least with respect to the electric field. Now, so that concludes our discussion about Chapter 7. And in Chapter 8, we're going to get more into some of the nitty-gritty stuff. We're going to start talking about things like capacitance and what have you. And I'll see you then.